Hello everyone, welcome to JCE Connect series of lectures. So in this particular lecture, I'll be taking the next case, that is a force exerted by a liquid jet on a moving curved vane. So in previous lectures and all, we have seen the force exerted by a liquid jet on a stationary curved vane. Uh, so here we are considering the force exerted by a liquid jet on a moving curved vane. In that, we have taken the first case, that is for a single vane. Single vane. Force exerted by a liquid jet striking on a curved vane when the vane is moving in the direction of jet. Let us consider a liquid of jet striking the vane. Striking the vane. This is a pipe. Through this pipe, a liquid is coming, and at the end of the pipe, a nozzle is been fitted. As you know, the nozzle function is to increase the kinetic energy of the liquid. When it comes out of the nozzle, it will come with a high kinetic energy, and this jet of liquid will be in the form of a circular rod. It will be having a very high velocity, and the moment it strikes, then this plate also start moving with a velocity u. Okay, so both are moving here. So here a relative velocity will come into picture. So what do you mean by relative velocity? The relative velocity, the motion relative to a other body. So if velocity is been taken with respect to other entity, that is called as a relative velocity. Okay, so here we need to take the relative velocity. In previous cases and all, we have taken the absolute velocity. What do you mean by absolute velocity? The motion with respect to a fixed frame. So we have taken the motion of a jet with respect to the fixed frame. So there we have considered the vane as a fixed one fixed entity. With respect to that, whatever the velocity we have taken, that is called as a absolute velocity. Example, if you take the motion of a train with respect to the platform which is stationary, is called as a absolute motion, where the train is moving with respect to the platform is a fixed entity. So with respect to that, the train is moving, that is called as a absolute motion. If the two trains are moving, say train A and B, then a relative velocity will come into picture. So relative to one another, motion of a body with respect to another body is called as a relative velocity. So here in these cases we need to take the relative velocity. So here a jet of liquid is coming out of the nozzle, will be having a velocity v. So this is having a velocity v. So before striking the vane, this velocity, what we call as a absolute velocity. The moment it strikes the vane, then the vane starts moving with a velocity u. Then it occupied a certain position like this, then it starts moving. As long as the jet will be striking the vane, this vane keep on moving with a velocity u. Then this u is called as a velocity of the vane. Then we have to calculate the again force in x direction as well as force in y direction. Okay, so the velocity of vane is u here. Then as the water gliding over the surface like this will be gliding over the surface after striking the vane. And again, assuming this surface is very smooth, there is no frictional loss. So then here also we are taking the absolute velocity. the jet will be striking with a velocity of v minus u. So here we have to take the jet will be striking with a velocity of v minus u, where this u is less than v, velocity of the jet. Then it goes out of the vane with velocity called relative velocity v minus u. Then again, if you resolve this one, you'll be getting a two components. So this is theta, and this component is v minus u cos theta, and this will be v sin theta. Okay. So again, as usual, we have to apply the impulse momentum equation to calculate the force in x direction as well as the force in y direction. Okay, so I think you understood this figure here. So again, in these cases we are considering the jet is also moving and the vane is also moving. So both are moving, so we have to take the relative velocity. Both are moving in the same direction, hence the relative velocity will be v minus u, and the velocity of the plate or the vane is considered as a u, which is less than the velocity of the jet. And the jet is striking with a velocity of v, then the plate starts moving, and the moment it strikes the plate, the water will glide over the surface of the vane, and this surface has been assumed as a very smooth. Hence there is no frictional loss here. There is no frictional loss, and the jet will comes out with a velocity called relative velocity v minus u. So here figure shows, right here figure shows a fluid of jet striking at the center of the curved vane, moving with a uniform velocity that is u, that will be less than v in the direction of jet. Let v represents absolute velocity of the jet, then A represents cross-sectional area of jet, and U represents velocity of the plate in the direction of jet. Velocity of the plate in the direction of jet. So when the jet strikes, the moving vane, when jet strikes the moving vane, the effective velocity is the relative velocity. Effective velocity will become the relative velocity, that is v minus u. Okay, so this is what we need to consider in case of moving vanes. So in previous cases and all, so where we have taken the stationary vanes, so there we have taken only the absolute velocity. Again, I am repeating, absolute velocity means the motion with respect to the fixed entity is called as a absolute velocity. Since in these cases both are moving, jet is also moving and vane is also moving, So we have to take the velocity of the plate with respect to the jet. Okay, so here the effective velocity to be considered as, that is relative velocity v minus u. So further we have to apply the impulse momentum principle here. So further applying impulse momentum equation, so applying impulse momentum equation. Now we have to apply impulse momentum equation. You know impulse momentum equation, the force in x direction, that is mass flow rate into change in velocity. So here the mass flow rate to be taken rho a v minus u. So in previous cases and all we have taken rho a v, but in these cases we are taking the relative velocity. You have to take here relative velocity into change in velocity to be taken initial velocity minus final velocity. Again rho a v minus u, initial velocity, that is, let us take this is a v1x minus v2x. Okay, so v1x and v2x. So again from this figure you can consider here what is the initial velocity to be considered here. So in this figure, look at this figure. So here we have to take v1x to be taken as v, that is the initial velocity with which the jet is v1x to be considered as v minus u. This velocity it is striking. When it strikes, it becomes v minus u, that is a relative velocity. With relative velocity it is striking. Then v2x is here minus v minus u cos theta. We'll get this one. Okay, in x direction. So we are calculating force in x direction. So mass flow rate, we have to take the mass flow rate or mass of liquid striking the plate, that is rho a v minus u. We have to consider this one. Okay, then here rho a v minus u into v1x will be v minus u. With this velocity it is striking initially minus of v minus u cos theta. Okay, so here it is striking with v minus u initially, then final velocity will be what, v minus u cos theta, but in the opposite direction. Then what it becomes rho a v minus u into bracket v minus u plus v minus u into cos theta. Take v minus u out, into bracket 1 plus cos theta. This is force in x direction. Okay, so this is a force in x directions. So we want force in x direction only. This is the answer. Then as we know how to calculate the efficiency, so now calculate the efficiency of the jet. Efficiency of jet. So efficiency of a jet formula, we have output by input. Please make a correction. In previous lectures I have taken, this is a reverse, that is input by output. So it's not input by output, this is output by input. Please make a correction. So efficiency of the jet to be calculated, output energy divided by input energy. So here what is the output energy? First we have to take the input energy. The input energy will be what? Input energy will be kinetic energy, what we are supplying per second. That is input energy. Here we are supplying the kinetic energy, that is the input energy. So how it can be calculated kinetic energy? The kinetic energy can be calculated half mv square is the kinetic energy, but it is to be taken per unit time. Then it becomes half rho AV into V square. So mass per unit time will be equal to rho AV into V square. It becomes rho A V cube. Rho A V cube. Now output energy. Output is what? Work done per second. This I explained in the previous lectures. What is work done? When you say the work done, the work we say the work is being done when a force acting on any body, if the body get displaced, then we say the work is being done. So in this case the jet is striking the vane, the vane is moving, means the work is being done. Hence work done per second, that is to be taken force into velocity. So this we have derived. So force, that is force in x direction acting, that is force exerting by the jet in x direction, into velocity of plate, into velocity of plate, that is Fx into u. So I'll substitute here Fx already we have calculated here. Fx rho A V minus u square 1 plus cos theta into u. Then work done per second, rho A V minus u whole square 1 plus cos theta into u. Okay. Then the efficiency of the jet can be calculated. Substitute here, that is work done per second divided by kinetic energy per second. Then rho A V minus u whole square 1 plus cos theta into u divided by half rho A V cube, kinetic energy. Okay. So simplify this one, you will get 2 times of V minus u whole square into u 1 plus cos theta whole divided by V cube into 100. So this is the equation you get after simplification. This is the efficiency of jet. Okay. Then further simplification, if you simply that one, means for maximum efficiency. How much is the maximum efficiency? For maximum efficiency, that is eta max. When we get eta max, we want eta max when differentiation of efficiency with respect to the velocity of the plate will be 0. Means the efficiency of the jet, it depends upon the velocity of the plate, how fast it moves. So it depends upon the velocity of the jet. Means suppose if you take a turbine, this is a impeller shaft, then the blades are mounted like this, then the jet will be striking. So this is the input energy what you are giving, that is the kinetic energy of the jet. Then this will be striking the blade, then the blade starts moving with a velocity u. it moves forward, then the next blade will come and stand before the jet. Again, that also receives a force, then that also moves, then again the next blade will come and stand before the jet. So this will continue. Then here the energy is being supplying from the blade to the impeller to the shaft to the generator. So the generation of power, electricity depends upon this blade velocity. Okay, then the efficiency of the turbine, it depends upon what? The velocity of the vane. Okay, so here the efficiency of the jet, it depends upon what? The velocity of the plate. If we differentiate the above equation, this equation, if we differentiate this equation with respect to the vane velocity, then we get the maximum efficiency. Then 2 minus 2 divided by v cube from above equation, 1 plus cos theta into 100, then d by du into bracket v minus u whole square into u equal to 0. So in this equation we have taken this only, v minus u whole square. In this equation we have taken only v minus u whole square into u. So this term, that is 2 by v cube 1 plus cos theta, it cannot be 0. Okay, so take only this term now. Only take this term and differentiate. So if I take d by du v minus u whole square into u, then differentiate this one. So let us apply here product rule, that is u into v. So v minus u whole square into 1 plus differentiate u. First I taken this, then differentiation of u will be 1, then take a u, then differentiate this term 2 into v minus u, then differentiation of minus will be minus 1 is equal to 0. Then what you get? V minus u whole square, then minus, simplify this one, 2u v minus u is equal to 0. Then v minus u whole square is equal to 2u v minus u. Then v minus u will be what? So this get cancels, you will get 2u. Then v equal to what? You get 3u. Then u will be v by 3. So velocity of the plate will be v by 3. When the velocity of the plate becomes 1/3 of the velocity of the jet, means this, when velocity of plate is equal to 1/3 of velocity of jet, then the maximum efficiency can be achieved. So substitute this u, that is u equal to v by 3 in this equation. Okay, we have to substitute that v by 3 in this equation. So what we get, if we substitute, then the maximum efficiency will be, when you substitute, we get 8 by 27 into 1 plus cos theta. So, look at this equation. If I substitute the value of u here, v by 3, substitute v by, wherever u is there, you substitute v by 3 and simplify it. If you simplify it, you will be getting 8 by 27 1 plus cos theta. Okay, then into 100. This is the maximum efficiency. So many times the question will be asked, prove that a jet striking a single curved vane at the center moving, the maximum efficiency will be 8 by 27 1 plus cos theta. Okay, suppose if theta is equal to 0, when you get a theta equal to 0, see, in this case, when you get a theta equal to 0 here, see, this is the curved vane, the jet is striking here. and the after striking, this is the uh, velocity of the jet exiting, making an angle of theta. When this theta equal to 0 means, suppose this is the vane. See, this is the vane. The jet is striking in this way. When the jet strikes, and then the water glides over the surface, and if it exiting like this parallel to the incoming jet, if these two are parallel, so in that case the theta will be 0. When the theta 0 means this plate will be what kind of plate it is? It is a semicircular plate. This is a semicircular plate. So in that case, when theta equal to 0 here, so theta equal to 0 means semicircular vein. Semicircular vein. When theta equal to 0, efficiency 8 by 27, 1 plus cos 0 is 1. Then what you get here? 16 by, you get 16 by 27. Okay, or efficiency you will get 59.2%. This is for single vein. Okay, so many a times this question has been asking in exams. Prove that for a semicircular vein, the jet is striking at the center, the efficiency is 16 by 27. So this is the proof. So when they are asking for a semicircular vein, you have to take theta equal to 0. If they are asking only for a curved vein, prove that 8 by 27, 1 plus cos theta into 100. Just you take the curved vein like this, then draw this figure like this, then derive it. If they are mentioning particularly semicircular vein, derive this equation, then you substitute theta equal to 0. So theta equal to 0 means it's a semicircular vein. Okay, so here the jet will be going out of the vein by making an angle equal to 0. That is theta equal to 0 like this. Okay, when theta comes to 0, you will be getting this one. Eta max is 59.2% or 16 by 27. Eta max equal to 8 by 27. Cos 0 equal to 1. You will get 16 by 27. I hope you understood this one. Okay, this is moving vein derivations. Very important. So I am creating here very important derivation. Derive an expression for efficiency, that is they'll be asking like this: 1 plus cos theta into 100. I'll show that. Many a times question will be asking. So here I can show you the question. You can see the question here in exam. Show that when the jet of water striking symmetrical moving curved vein at the center, the maximum efficiency for a semicircular vein is 8 by 27, 1 plus cos theta. Okay, so this is the derivation, that one. So this is the 1 plus 8 by 27, 1 plus cos theta by 1 plus cos theta into 100. Okay, so look at here like this. Okay, then again if they are asking in terms of efficiency like this, percentage, you 59.2 percentage. I hope you understood this one. Okay, practice this derivation. This is very important. Thank you.